The lecture from Monday, the video didn't work. And so all I posted was audio. So I went to look at the created movie at the end of the lecture, and it said there was some error. Now, the weird part about it is I just started it up this morning, and the movie appeared. So I'll re-merge that audio and video and post it this afternoon along with today's lecture. A reminder that the exam will be 1 week from today in class. I had said 8.5 by 11 page of notes, handwritten, single-sided. Live it up. Go double-sided, okay? So I'll update that on Piazza. So 1, double-sided, handwritten, eight and a half by 11. And yeah, and I'll want that turned in. So I'll give it back to you when I give you back the graded exams in case you wanted it for some reason. So we talked on Monday about, we finished up normalization, regularization, talking about dropout, right? And dropout, parameter sharing, ensembles, and then we went into batch normalization, right, which is this mechanism for changing the mean and standard deviation of each incoming activation. So normalizing that to 1 and 0, and then scaling it to some learnable desired mean and standard deviation. And then finally, we talked about gradient descent optimization algorithms. We talked about the simplest one, which is just use the gradient as the amount you're going to move. So the gradient times some learning rate. And what did we look at next? All right, what's the disadvantage of that if you look at something like a bowl here, a very ugly bowl, the contour lines, right? That if we look at our axes, our gradient is highest in the vertical axis and is less in the horizontal axis. So that means we're going to take small steps to the right and large steps up and down, which is going to ping pong us back and forth and back and forth. So one of the solutions we looked at was momentum, right? So the idea is rather than just using our gradient times the learning rate as our movement, we go ahead and keep a running gradient and use that. So if we've got slow but steady changes, that will build up more and more our velocity that we'll be taking each steps. And if we've got large changes, but they change direction, then they'll tend to be canceling each other out. And then we added on Nesterov momentum, which made a slight tweak to it and just said, instead of calculating the gradient where we are and then adding that to the velocity and then moving by that velocity, we're going to start where we are, we're going to move by whatever the velocity is, and from there we'll figure out what the right gradient is. So it's a little farther along, so we have a better prediction of what the gradient is. Okay, so I'm going to talk about some other optimization algorithms. And let me just say that there's a whole field of designing optimization algorithms. Okay, one that I'm not mentioning here are, using second derivatives. Derivatives, yes. So using the second derivatives as a way to find out what the shape of your, where you are, and that will help determine whether you wanted to use a larger or a smaller jump in those locations. Okay. So we're going to look instead at per parameter learning rates. We're going to look at, in this bowl case, a way where we could say we'll use large gradients for the horizontal axis and small gradients for the vertical axis. It's not what I mean. What I actually mean is large learning rate for the horizontal axis and small learning rate for the vertical axis, because we don't have control over the gradients. The gradients are sort of as they're given here. So we're going to keep a learning rate per parameter. Again, by parameter, we mean each weight, each bias. And then we're going to reduce the learning rate if a parameter has had high gradients. Okay? So the larger the gradients that have happened so far, the more the learning rate is going to reduce. So what we're going to look at is then the change in some parameter is going to be, normally it was our learning rate times our gradient. And we're going to now divide by the sum of squares of our previous gradients, plus an epsilon to avoid the potential to divide by 0. So just keep track of all the gradients we had so far. Sum of squares. If we've got large ones, it's going to reduce the learning rate. Yeah, Drew, you have a question? Large sum of squares will cause this to be large, which will drop the learning rate, basically, the effective learning rate for this particular parameter. Okay? And this is all parameterized based on, we should have sort of a t here too, in terms of this is the derivative with respect to WT. Right? So this is all for this particular weight. Any disadvantages to this? Now, what happens to the learning rate for a given parameter? The effective learning rate. What does it look like? It drops over time, right? It starts at the specified learning rate, and it can only go down. So it's monotonic, non-increasing, right? Which could be a problem, right? Maybe we're at a point in our space where, for that particular weight, we're having a lot of large gradients. Okay, so we've got steep and shallow, and then we move into an area where it's very flat. We're going to be moving inch by inch because we got penalized for all those old gradients. So a solution might be just keep the last k gradients for some k. But that's expensive, right? This isn't so bad because we can just keep our running sum of squares. Right? So every new gradient just add to the sum of squares. So we just need to keep one extra number for every parameter. If we're going to keep k different gradients, then we need k different numbers for each one. And that just takes up, k times more space. So how do we deal with this? How have we dealt with this in the past? Exponentially weighted moving average. Right. And so before we get there, though, so infrequent updates have a larger learning rate. Large updates of a smaller learning rate. That's the good part, right? So it will be adaptive, right? Adaptive gradient, Adagrad. The disadvantages is it's monotonic, non-increasing, and which means it may get small over time. So our solution is what I was just describing, and that is RMSProp. So we're like Adagrad, but we don't keep the sum of squares. We just keep a weight decayed average. So we say our average is going to be a weighted, right, based on gamma, of our weight so far plus the square of the current gradient. So nothing, it's basically like Adagrad, except we're using this exponential moving average. And then we just used that instead of the sum of squares. So, is this non-increasing? No. If we have a situation where we've got high gradients over here because we're doing all this movement in this direction, then for that time period, we're going to have a large E sub t. But over time, as we go into shallower and lower gradients, we'll just lose the effect of those large gradients. Okay, this is RMSProp. The funny thing about this is there was no paper for this for a while. It was instead in a course video that Jeff Hinton had done. And he said, this would be a good way to do this. And so then there are references, basically, which I think is interesting, just to that video. But eventually it did get written up. Does that make sense? OK, now what we can do, so this is better, because the per parameter learning rate can increase or decrease. Right? It just looks at the recent history. How do you affect how big that history is, right? How much effect the history is? Right, let's say, yeah. It's exactly based on the gamma, right? So if we have a very high gamma, then we're going to be using the history a great deal. All right, and then we do something very simple, and we say, let's take RMSProp and let's add in momentum. Okay? This is called ADAM, Adaptive Moment Estimation, and that's all it really is, RMSProp plus momentum. So we have a velocity here, which is weighted, and this is basically the E from the previous one. Right? And then, sorry, this isn't the E from the previous one. Here's the E from the previous one. It's exactly the E from the previous one. We have our velocity, right, which is our weighted moving average of our velocity. And then we what am I doing here?
These are adjusting to make sure that the initial elements aren't really small.
Adjusting so the previous elements aren't really small. Let me think about this a second. So give me an example.
Well, like when you're doing an exponentially weighted moving average, the first element is 1 minus beta times the thing, and so you want to adjust for that.
Okay, that it is reasonable. I don't know where. I forget about it.
You don't want to be averaging with a value with a bunch of values of 0 beforehand.
Okay, that makes sense, so that when we start out, we don't have a bunch of zeros. And so what we end up doing is we say our parameters are equal our old parameters minus the learning rate I'm sorry, this is just looking crazy to me for a second. This is not, yeah. So let's go back to our RMSProp for a second. Okay, and here we had the learning rate times the derivative. And we now want the learning rate times the velocity. And so I'm going to put in here, and I will come back to you on Monday and make sure I've got this right. So we want the velocity. And here, we want that. So that should be right, but I will double check this. So ignoring the velocity, right, in the RMSProp, we had the gradient here, J prime. And now we say we don't want to use the gradient directly. We want to use the velocity where the gradient has been applied to the velocity. And so that's what we have. So it's learning rate times the velocity over the square root of the weighted sum of squares, so the moving average, plus again some epsilon so we don't divide by 0. So this is very popular. So let's see. We had per parameter learning. We added in a weighted average, and then we added in momentum. What else could we add that we've seen? Say it again. Not for learning rate. So just sticking with our optimization algorithms. What did we see on Monday? Right? First, we just took the gradient times the learning rate. And then, what was the next change we made? We did talk about stochastic, yes. So all of these can be applied whether it's stochastic or whether it's an entire batch. We talked about it like when we were going over a recap a few minutes ago. The next thing we added was what's this term? It's our this whole thing is our velocity, which is what gave us momentum, right? And then we made a small tweak to that. What was the small tweak? Nesterov. So why not add Nesterov here? So basically Nesterov plus atom equals, well, I don't know, what would you call it? An atom. Okay, so if you look at PyTorch or TensorFlow or any of these, you have lots of different optimization algorithms that you can choose from, and that's basically a hyperparameter, is what optimization algorithm are you using. But atom's a good start. Questions on this? Okay. Now for something completely different, neural style transfer. So a couple of years ago, I think 2016, an interesting paper came out showing how you can apply the style of one picture to another picture. So we take the semantic content of one image and re-render it in the style of another image. So here's an example. And the fact that this part is cut out, just sort of ignore that. I was missing one of the lower left corners of one of these images, and so I got rid of it. So here we've got, this is from the paper. It looks like an old town in Europe, okay? That's the original. Here is the style that we want to be using. So this is the desired style. This is Starry Night, I think, from Van Gogh. And now what we want is this, but kind of looking like Van Gogh did it, right? So, well, there it is, right? It kind of looks like that. We've still got our houses, and we've got the tree here, although it looks pretty different. But we've also got our swirly suns, and it's all done in the right colors and so on. So that's what we're going to learn about today. Questions on what we're trying to do? If this were the style that we applied to this, that'd be completely different. Yes. So content from here, style from here. And we're going to have to decide what does content mean and what does style mean. And really, when we come up with it, it's going to be kind of what looks good. Lauren.
Is it harder to go from like a more detailed, realistic thing as a style if you're like, because this is going from something very detailed, realistic to a more abstract style. Is it harder to go the other way?
Let me just jump ahead. That's a good question, okay? So here's an example, again, from the paper. Where we've got, help me out, one of these is New York and one of these is London. I think that's New York. Yes. And this is London. And so we're looking at London at night looking like it was New York. So it's an interesting contrast, right? Where we don't have a hugely stylized, it's still fairly stylized in some way. But if you didn't have kind of a stylized style image, it'd be hard to see what it should be, right? So I think this is a good example where, yeah, it works reasonably well, where these are photorealistic rather than very sort of abstract. Okay, so that's the problem. Here's the idea. We use an existing neural network trained on ImageNet. We're going to use, I think, VGG. The notebook I'm going to go through is, I think, VGG 16 or 19, something like that. Okay. We take this rendered image. That is this one here. And we started out as some initial state. What's a good initial state? Random, white noise. So we'll just set this up as white noise. It won't look this good, right? It'll look like white noise sounds like. This is the right word for something visual that's like white noise. White. Yeah, anyway. We initialize it to random. And then what we're going to do is we're going to create a loss function. And that loss function is going to measure how close is this image to the original content. So content-wise, how close is it? And style-wise, how close is it to the style image? So we're going to have two measures of loss. We'll add them together. That'll be our loss function. And as it's doing these calculations, of course, it is looking at the values in this image. And so we can take the gradient, that is the derivative of the total loss function. So we're going to go ahead and combine these. I was going to say sum, but we probably want a weighted sum. So combine these for a total loss. And then take the derivative of that total loss with respect to every one of these pixels. And so what does that tell us? It tells us how to adjust the pixels to make it better. And so that rendered image is now going to go from white noise to slightly less white noise, slightly closer to the content, and slightly closer to the style. Now these are probably neither of them going to be, we're getting closer to the pixels, right? We're not saying that the top left pixel of the content is what we're trying to match here. We're going to have to come up with some other measure of the content and the style that's not going to be pixel exact, because otherwise they're just going to be fighting each other. You know, to say, the content will say, I want it to be red, and the style will say, I want it to be blue. Does that make sense? So it's this as yet unspecified way in which we're going to measure content similarity and style similarity. Yeah, Bill.
Are we defining a business metric that measures the closeness of the rendered image, like content versus?
You're saying you would like to see how to do that? Okay, let's do that. Let's say we want to know how close. He didn't even read ahead. This is great. So how close is it? Let's try and come up with a way. So we want to say, how close is the rendered image content-wise to the original? We don't want to measure the pixel differences, right? That just won't help us very much. Instead, we have this neural net, remember? In fact, we didn't even say what we did with the neural net. We had a neural net, and then I just kind of ignored it. So let's use the neural net. So we're going to take the neural net, and we're going to feed through our content. So here's our content. Right, see how nice looking it is? This is probably my best image I've done all year so far. So we're going to feed this to the neural net, right, where the neural net has a bunch of layers. And we get some output. We don't care about the output. I don't want to know whether it's a cat or a dog or a fish, right, or a bird. Not interested. Here's what I'm interested in. I'm interested in this layer of activations. Okay, so this is going to be layer K for some K. If I look at these activations, that will give me some idea of what the content is of this picture. Right? These activations control completely what the output is, right? Right? These are all calculated based on previous layers, but the succeeding layers can only work based on what they get from here. So this has some measure of what the content is of this, because I know it's going to be able to tell me it's a happy face, assuming that's one of the categories. Right. We just don't care about the classification, though. which layer do we want to take? What if we took layer 0? What is layer 0? It's our image. What's our loss probably going to be? You know, I mean, if we had, let me back up a second. That doesn't, we are taking the loss with respect to 2 images, right? We're looking at content loss, and it says, here are 2 images. How close are they? So for now, I'm only looking at the content. So this is the content, and we're going to get our activation. We don't want layer 0. Let me make this a little more clear. So we're going to, what color is that? We're going to run the neural net twice. On the first time, we're going to feed the content through. The second time, we're going to feed in not the style, but our rendered image. Or another way to think of it is, our content loss function basically says, image 1, image 2. How close are these images? Here's image 1, and here's image 2. And image 2 is not so good. Image 2 looks like a bunch of white noise. Okay? But we're going to feed this in to the neural network, and we're going to pull out this same layer. So we pull out the same layer for one image, the same layer for another image, same neural network, and we're going to compare in a way we'll have to look at what these values are. Does that idea make sense? Okay, so if we were using layer 0, we would just be looking at the differences between the pixels.
Image 1 is the original one, and image 2 is the randomly started.
Yes, yes. But the way we're defining content loss, we can apply these to any 2 images. The way we're going to use it is we're going to have one of them is going to be the content image, and the second image will be the rendered image. If we think about the features that our convolutional neural network learns, in the first layer, what sorts of things is it learning? Low-level features like a line, maybe a diagonal line, or something about the color maybe. And then as you go layer by layer, it builds up sort of larger and larger structures. Okay? Somewhere in there we know there are neurons that recognize particular kinds of dogs, right? Because we've seen some pictures of that where it's like, oh, these are fluffy dogs and these are what look like car wheels and some other sorts of things. So as we move, this is going to get higher and higher level, right? Because at the very last level, we know what we're getting is enough that it can fairly easy to decide, is it a house, is it a bird, is it a plane, is it a train, so on. So where do we want to be in terms of our layers here for deciding the content? We want to be to the right, right? So we'll be somewhere over in the right third. Last layer, next to last layer, something like that. I take that back. We actually have, in VGG, we have blocks that we're working on, okay, where we do pooling. We do some stuff, we do some pooling. We do some stuff, we do some pooling. Do that about 5 times. We'll just stop right before one of those poolings. So we'll do either the last one or the next to the last one. But that's the idea. Stay over to the right. So far, what we've got then is, we've got a set of activations for one image and a set of activations for another image. And they're from the same layer, so they're comparable. Those are tensors, right? Those activations. It's a tensor of, let's look at this a second. So it's n by m. What the heck is n? The what? It's not the neurons. It's the, yeah, rows column. So this is the, I think it's width times height. And F, you're up now, Lauren. Yeah, so this is the number of neurons or number of convolutions, right? Because we have F features at this particular layer. Right, so this might be 5 by 5 by 120. We'd have to look and see what the VGG is, right, and remind ourselves of that at what particular layer. So, but I'll just kind of throw this as a, for example, it could be 5 by 5 by 256. So each n by m slice, and it's really n by n, because in our cases they're square, right? Our height and our width are the same. So we've got n by m, except it's probably the other order around, by f here. So let's go ahead and take this first slice here, right? So that's, does that make sense? Kind of, it's not. This first slice is n by m by 1, okay? We're just going to stretch it out. So we take that and we convert basically n by m by 1 to flat vector, okay? So this is a given feature. We don't exactly know what this feature is. This might be the feature that detects lions. I don't know, right? So this is saying there's a lion. Actually, let's look at this one here. What does this say at the top left here, assuming that this is a lion detector, a lion feature detector? What's it saying if this was highly activated in the top left? There's a line where? There are actually no lines right here. In approximately the top left. We have to look at the receptive field for this particular value here to see how many pixels do that correspond to in the original. The farther we get down in the layers, the larger that receptive field is. But there's a line somewhere kind of over in the top left. So that says here there's a line somewhere over in the top left. What we're going to do then is we're going to take this n by m, and we're going to do this for image 1, and we're going to calculate the same n by m, for image 2. And then we are going to just do a pointwise multiplication, add them together. Okay? So if this was big, that meant there was a lion in the top left of the first image. And if this one is big, that would mean the same thing, right? There's a lion in the top left. So we multiply them together, and if we end up with if they're both big, we end up with a squared big number, right? So we're going to go through and do that multiplication and basically say, how well do these correspond? How will these correspond, right? Do they both have large when the other one is large? If one of them is large and the other one's small, then that means no. One of the images had this feature going off here, and the other image didn't. So that's a mark of dissimilarity. But if they both have either large or small activations, right, highly negative or highly positive activations, then that means this feature's firing in the same location in both images. Does that make sense? And we're doing this across all the features, right? So across all f of these. So that says all the features that this neural network knows about, we're going to try and compute for each feature how close are we to having the same features in the same areas. And we've got some flexibility, right? Here, this is a line in somewhere in the top left. Let's say it's maybe the top left. If we moved it backwards, right? If this is 5 by 5, this might be in the top left 100 by 100 pixels. So yes, we've got one there, and yes, we've also got one here, but do they need to be in the same location? Do the lines need to be identical, right? Do they have to have the same number of whiskers? No, right? All right, so we end up with a single number. Yeah.
Is this sort of point-wise sort of unification of the layer only something we do for the style, or just for content?
We're all. What just happened here? Hold on a second.
I think when you were drawing, you accidentally skipped from the content-wise to the style-wise.
I see. That's not really what I want to do. Yeah, that's not what I want to do at all. Okay, so what we just did, just sort of like hold that. We're going to come back to it when we get to styles. We're now going to content. All right? I'm sorry about that. So boy, oh boy. All right. So we're going to look at a later layer. We understand how we fed them through. We pulled out the activations at a particular layer. And here's an example, by the way, from the paper showing our original image. And then what happens if we do reconstruction of the image. So it's based on similarity at an earlier layer. So here, this is at a very early layer, and we're looking at another image that is similar to it, that we created via backpropagation. And you can see here, it looks a lot like that does, right? It's very sort of pixel accurate. As we move into a later layer, it becomes a little less. It's hard to see here. It's maybe a little blurrier. But as we move on, it's getting kind of janky, right? The windows are not quite straight. And as we move on here, or even here, it's getting farther afield from where we were. Okay? We still get the idea. It looks like the same sort of thing here as it does here, but the details have been fuzzy, right? And the fact that we got something like this might have had to done with the random image we initially generated. So kind of where it came from would lead us to where we go here.
Are these the rendered images?
So across the bottom, we have the rendered images, ignoring style. This is just saying, let's take a random image, white noise image, and a content image, and use backpropagation to try and update this random image to be close content-wise to the content image. And this is measuring content similarities very early on, and this is measuring content similarities later on. So we can see kind of what it looks like. This is more high-level content, and that's more low-level content.
So what loss function are we using?
That's a good question. What loss function do we want to use? We can really just use sum of squares difference.
So just some generic loss function.
Yeah. So we'll use sum of squares, let's say. Okay, so this is fairly straightforward. We just say if we have, and it still works, my example, the lion. Okay, so we have a lion up in the top left of the original content. We'd like to have a lion over in the top left of the content of the random image. And so therefore, if we're high in one and low in another, that'll lead to a higher loss. And if the two values are close, that'll lead to a lower loss. So that's the content. So we don't have to do any particular unrolling or anything else. We just take all the activations and then just do point-wise difference, square them, add them up. Questions?
so you want to use like a later layer, right?
We want to use a later layer, exactly. If all we were looking at were how close can we get our original image to be this one, then we'd want to use an earlier layer. But we're not interested in the exact details of the exact pixels that are this. We're much more interested in the underlying structure and content of it. We'd rather it be fuzzy, like this might be a little too fuzzy, maybe this one would be somewhat better, but the fuzziness here is nice because it gives us more freedom. And the freedom is going to allow us to apply style to it too, right? We don't have a lot of freedom here. Because the pixels have to be, if the pixel's wrong, it's wrong. This allows us to move things around, to have lions with different number of whiskers and stuff like that, possibly. Okay? Because it's the higher level features we're interested in. All right, now the style. So earlier layers measure low-level stylistic choices. Like probably the earlier layers are going to be determining things like colors that are used. And then later layers measure high-level type features. Like, let's go back to here. Like maybe these, oh, these are stars, right? Because starry sky. Yeah, so these are stars. So the presence of these stars might be found in higher layers. You had a question on that?
So looking at that, it's obvious that like, there's more to the style image color differences, but if we had a style choice, that would basically like a low level representation of like something cool colors, then would we not want to avoid going in too far to the right?
So it's interesting. For style, there are sort of small, specific style features. In here, I would say to be things like the color palette, right? We're ignoring a large amount of the color palette and using mostly blacks and blues and yellows, right? So that's something that could probably be found in a very early layer. Whereas something like this, whatever that thing is, or the stars, or kind of the swirling look to it is probably happening in a later layer. So we want to capture the style sort of everywhere, okay, at both earlier layers and at later layers. All right. And here's the key on how this is going to work. Key number one is we're going to assume our style is consistent throughout the image. We're not going to say, is it blue up towards the top left and green up down towards the bottom right? We're going to say that, if it's blue swirls, we don't care where the blue swirls are. Some features in a layer are co-occurring. For example, and this isn't necessarily true for this particular style image, but you can imagine a style that had a lot of blue ovals. Okay? So maybe I've got a layer in my neural network that has both blue feature and oval feature. And I want to capture the fact that that blue ovals happen together, that they're blue ovals and not some other color. So I want to look at how two features interact with one another. And so let's say this is blue and this is oval. Right? So this is a particular set of activations at a particular layer, and we just happen to have a 3x3 to make it simple. So if I have, I have some blue up here, and here, and here, and I have oval here, and here, and here, that kind of means blues and ovals go together, right? Because they occur only when the other one occurs. If we had a missing oval here, then we'd say blue ovals mostly occur together, right? So when you see an oval, you see blue. When you see blue, you see an oval, for the most part. There's some it's not as high as it was here. And this is kind of what we're going to capture. For every pair of features, we're looking at and say, how do they co-occur with each other? And guess what? The way we're going to do that, we're going to unroll our features. Okay? So, but we're going to make something different. In fact, I'm going to erase this for a moment and put a brand new slide. Okay, so here's what we go. We've got our tensor, n by m by f, and we have a particular slice of that tensor here, and we have another slice, let's say here. Okay, so we've got this, and we've got that. Okay, so these represent two different features, and the locations within this rectangle represent the locations in our original, right? They're spatial information. So we are going to convert this now. So this is n by m, and this is feature I, and this is feature j. Okay. And this is all within, again, a single set of activations, a single layer. We unroll this, and we get and we unroll the orange one, and I'm going to put it below, and we get this. And now our goal is determine how co-occurring these two features are, ignoring spatial. So we don't care where it's occurring. We just want to know that we have blue ovals, for example. And so this is where we're going to do our pointwise multiplication. So we will we should make that a different color. So we multiply them together, and and that equals kind of, this is feature I times feature j at the top left. Feature I times feature j at the next location, at the next location, the next location, and then we sum them and we get a single number. Yes?
Sorry, I'm a little confused. So feature I and j, are these corresponding to the rendered image and the style image, or just one single image?
One single image. So we're looking for a single image. We're just saying I'm giving you a picture. What's its style?
So this process is done for the style image and then for the rendered image.
Exactly. Exactly. That's what's going to happen. So we're doing it now. Let's just consider it for the style image. We're thinking of it that way, but we will do the exact process for the rendered image too. So in fact, let's just think about it a second. If we come up with this number for the styled image, that's going to tell us how much do these two features co-occur. If we calculate the same thing for the rendered image, how much of those co-occur, we'd like these numbers to be similar. Okay? This tells us, though, only for a given ij pair. And we want to do this for all the features. So we want to come up with a matrix that says for every feature I and every feature j, how much do they co-occur?
Do you ever do like 3 or 4 features co-occurring?
Not, the paper doesn't, and I don't know that anyone has done that. This works surprisingly well.
So say the reason we did, like we did in the content to like render comparison, we didn't use the like sum of different squared, because we only care that thing happens and not where it happens.
So for the content, we do care where things happen.
But here we don't.
Here we don't care where things happen. We're throwing away the spatial information.
But how is pointwise multiplication? It still like takes like the pointwise.
So once we multiply them, we still have spatial information. And then we just throw away the spatial information by summing them. Okay? And that gives us a single value within this larger matrix.
Would it be accurate to say that style transfer is basically like an optimization problem where you're trying to make your new rendered image as close to both the image of the rendered?
Yeah, it's an optimization problem where you're trying to reduce the loss, and we're defining the loss in such a way that it's the how different are we content-wise from the content image and style-wise from the style image. Okay, so what does the diagonal of this matrix represent? The same feature. And so what is that number going to represent? What does it mean if we have a big number versus a small number? See that? Okay. Evan? Presence or absence of that feature, right? If we wanted to look at it in a binary fashion, right? How much does this feature happen? In this case, if we find the blue feature, I'm sure that's going to be big for Van Gogh.
So by doing this, like, co-occurrence of features calculation we get for free, also just the occurrence.
Yeah, but we get the single occurrence of the features too. Yeah, okay? So this is called a Graham matrix. The fact that it's called a Graham matrix doesn't really matter. It just happens to be. And probably what happened is the guys, created this and went, and they're going to publish, and they take someone to look at it, and they say, oh, yeah, that's a Graham matrix. All right, we'll put that in the paper. So, all right. So we're going to make one Graham matrix per layer that we choose to use, per image, because we're doing 2 images. Okay? Does that make sense?
Sorry to stick a little off track, but it seems like when we're computing our loss, I'm presuming that we're computing our loss based on these graph distinctions, right? It seems like we're weighting co-occurrence of features as f times as important as single occurrence of features because there's that many cells. Like approximately, is that correct? Do we want to do any weighting to correct for that, or is that just fine?
It's just fine in the sense that the pictures look good. And there's we don't have any other description. There wasn't even a talk of that in the paper, I don't believe. So, yeah, because we've got basically f occurrences of the diagonal and f squared over, f squared, because I think we use the entire matrix. So f squared, so yeah. It's a reasonable question, and that's something you could look into. Okay, so we've got this Graham matrix. This says, so this is the co-occurrence of feature 1 and feature 2, right? So it's a measure, which happens to be identical to the one here, because our co-occurrence measure is symmetric. All right. So let's look at the style looking at different layers. So for example, we're going to do the same sort of thing. We're going to do a reconstruction from a random image starting at an early layer, and we're going to get something like that. And notice it's small features. It definitely doesn't have any swirls like this, no swirls in fact at all, because it's looking at small little areas, right? And these are the low-level features. It hasn't learned high-level features. Here it's learning a little bit higher, and a little bit, and a little bit more, and a little bit more. So what layer do we want to use? Use them all. Let's just use them all, because the small things matter too, right? Here we're going to lose some of the detail, and part of what makes a style is the details, right? If you've got a Monet, you want the little dots. So our final loss is going to be, and we do have to figure out for these gram matrices, we've got a gram matrix for image A, a gram matrix for image B. How do we want to define the loss here? And maybe that will just be sum of squares. And then we'll just maybe add that up for all the layers. So some alpha times the content loss plus a beta times the style loss. And we can see here a missing content image. There's the content image. So it's not the last. So we have our content image here and our style image, and we look at different values of alpha and beta. And I wrote down let's see. So this is the ratio of alpha over beta. Okay. Say it again?
I think the style loss should be past image, comma style, not image, comma content.
This is definitely a typo. Yeah, that'd be better. So we can see here, clearly this is more style. And as we move our way down, a little more content, a little more content, a little more content. Questions?
Alpha, beta, how do we come up with that? Is that something we learn through the process?
No, because you don't have any good, you look and you say, which one do you like? And which one do you like? This one. So that'd be good. Use a beta that's 10 times alpha instead of 1,000 times alpha. So trying to think why I actually want to show you this picture. I showed you the first half, I showed you the second half. I don't see anything to gain from showing both of them, right? Other than the fact to just show that we are using the same neural network. Okay? Yeah.
Does that make the difference, the actual computation of reconstructing the content versus the style?
The computational difference between calculating the loss, do you mean calculating the loss of the content?
I assume for the content reconstruction, applying the inverse mapping, how we do the style representation.
So the way these reconstructions are working is we take a random image, we take our content image, we calculate the content loss, and then we take the derivative of that content loss with respect to every pixel in the reconstructed image. Okay? And then we do it again and again and again and again and again. And that image will get closer and closer and closer. The content loss definition is parameterized on what layer we use. And so therefore, if we use an early layer, we're going to tend to get pixel perfect reconstructions, whereas later layers are going to be higher semantic content.
What's that?
We do exactly the same thing and say, for these pictures, this is only using the style at a particular layer.
How come that looks nothing like the first picture, the input image?
Which A, B, C, D, or E? A, if you looked at this in a magnifying glass, right, and you looked at just areas of, I don't know what the number is going to be, 9 by 9.
Zoom in something?
What's that?
Were you zooming in on something?
I'm not zooming in, but the way we're measuring our style loss, right? So let's look at the first layer. We have our convolutional neural network, right? Our input is, let's say, 288 by 288. We will max pool that down, I don't know, in our first layer, I don't remember what the number is for VGG, but we may have 128 by 128 by 50. So we've got 50 different features at 128 by 128, right? With a 3 by 3 convolution. So that 3 by 3 convolution means that the first layer, every convolution, every feature at a particular location is just looking at 3 by 3 pixels. So its receptive field, the number of pixels it sees, is very, very small in our first layer. And that's why we have very, very detailed. Does that make sense? Okay.
Why do we initialize to white noise as opposed to being potentially closer to our goals, such as like either the content image or like the image
That would be such a good idea to experiment with initializing rather than white noise to the content image or possibly the style image. So consider that part of your assignment because it's actually in there. And I believe you'll probably find the results are, if you start with the content image, it'll end up closer to the content image. And if you start with the style, it'll end up closer to the style. What's that? How do you know what the middle is? You have a special experiment to try, okay? So just take the average of them and see what happens, and put it in your notebook.
So if you decided to use the content image, would you be able to get features? Because my understanding is learning extracting the features of the content of the content image is part of the first part of it.
So I'm not sure I understand your question. If we started with the content image, then
we would have zero loss and we wouldn't be able to.
no, we'd have zero content loss, and we'd have a very high style loss. And therefore, it would the style loss would pull us away from our pixel perfect image, is what would be happening. Right? Because you will agree that the Van Gogh and the original content are not very close stylistically. And so therefore you have a very high style loss, and the sum of the losses then will be high, and the gradient will tell us, get away from that content and move towards Van Gogh. Okay? That's what will happen. All right, let's look at the code for this. So there's a style transfer notebook. This is in the CS152 Git repository now, so just do a git pull, and you'll have access to this. You'll remember that when we use like the VGG model or the ImageNet, we have to do a transformation of our input images, right? So the input image gets transformed by normalizing our input, right, based on the mean and standard deviation of the red, green, and blue channels. So that normalization happens for us relatively automatically. There is a somewhat corresponding denormalization. But what the normalization does is both does that normalization and adjusts the order of the columns in the tensor, columns isn't right, the order of the dimensions in the tensor to match PyTorch. So what we feed in is like 228 by 228 by 3. And what we get out is 3 by 228 by 228. Okay? Because PyTorch likes the channels first. It's just a choice they made because they think their convolutions or their GPU optimized stuff runs better. So all this does is denormalize. The denormalizer does the other stuff we talked about, the mean and standard deviation. And then this move axis changes the dimensions. We want to be able to draw an image with a particular size, so we're looking, these are matplotlib calls to do that. We want to create a random image, so we just create a random image based on a given shape that's coming in. Right? So a shape is a tuple of like 228 by 228 by 3. And so we just create our random white noise. We're going to do some scaling later. So basically, if we think about it, our style image and our content image may not be the same size. We want a style image that is at least as big as the content image. And so this scales, we'll use to scale our style image. So it's as big as the content image. If the aspect ratios are different, then there may be some extra style image along the bottom or the right. So we may lose some of the style image, but that's okay. All right, so how do we convert a random image to resemble the content of another image? We're going to use VGG16, and we've got a house. In fact, this is my house. So it's like 1600 by 1200 or something. It's fairly large. And here's what we're going to do. So we're using more PyTorch stuff than we are FastAI for this. So closer to just raw PyTorch. So Arc is our architecture, which is VGG16. So we instantiate a VGG16 model. True means we like it to be pre-trained. Okay? So the first time through, it'll download the weights. We haven't done that already. We move this to the GPU. This is stuff that FastAI hides from you, which is kind of nice. And we evaluate it, and that gives our model. I'm going to call this the full model because it includes all the layers of the model. And we don't want it to be trainable. We're not doing any training, right? We just like the network as it is. We're going to be training something entirely different. We're going to be training image. You, be better. Be more stylistically like this other. Okay. Transforms from model basically says for VGG16, and for given you want, let's say 228 by 228, it constructs you training and validation transforms. This is a FastAI call that's doing this. We don't really care about training or validation. We'll just use the validation transforms. So here's what we're going to do. We're going to convert the content image. And we see now we get a 3 by 288 by 288. Okay? So that's done the normalizing of the red, green, and blue values. It's resized it, and it's redimensioned it. And now let's create a random image. Well, how do we do that? We just call our random image, and we show it, and it looks like white noise. Now what? Now we want to do the same. So opt image is our random image. We're going to go ahead and apply our transforms, and then we have our opt transformed image. And V means create a variable, okay? So it's a PyTorch call to basically say create a variable from this tensor, and we want a gradient, okay? So for all of our 3 by 288 by 288 values, we're going to get gradients for them, so we can make them better. The none here makes it actually a 1, because we're doing, the network wants to work in terms of mini batches. And so the first dimension here is how many x's that we have. And in our case, we just have one. Yeah. The val transforms are the ones that will normalize based on the ImageNet mean and standard deviation of the red, green, and blue channels, and resizes and changes the channels. Okay. All right. Let's look at the model. So the model does a bunch of convolutions, batch norms, ReLUs, convolutions, batch norms, ReLUs, and some max pools every so often. And how can it have 43 layers when we said this was a VGG 16 or 19? Yeah, we're just counting convolutions. So, okay, so let's create a new model. So a sequential model just takes a sequence of modules and puts them together. So we're going to take the children of our model and take all through the 37th layer. The star or splat operator converts this list to a bunch of separate parameters. So it just says we have 37 separate parameters here. And that is our new model. Okay. So we just chopped off the last several layers. The reason we're going to chop off the several last layers is so that we can actually look at the output. That's the output of that 37th layer.
So 37
It's true.
is like a K.
37 is exactly our K. Yep. All right, so we take our content image, and here's one thing. Our content loss function, we don't want to keep recalculating the activations for the content image because it's not ever changing. So we're going to one time calculate the activations for the content. So that's what we do. We're going to turn the content transformed image. The none adds in the one dimension at the beginning because we just have one example we're putting through. We convert it to a PyTorch variable that doesn't require a gradient. So that's the VV instead of V. And we run it through the model because our model is a function that we could just call. And it returns us, what is this? Its shape says it's a 1 by 512 by 18 by 18. What's the 1 mean? One example. 512? The F, the number of features. The N and the M, the width and the height. Okay. And now we're going to start optimizing. Right, we're just about done. We're going to do 1,000 iterations. And we're going to use a different optimizer from the ones we talked about. This one happens to use the second derivative. It takes a lot of space. It works well for this particular problem, and it's the one that they used in the paper. So we're going to use a learning rate of 0.6. And we are optimizing. This is just a list of parameters to optimize. So we're optimizing our random image. Our content loss, we're going to use mean squared error. Right? Square the differences. Times 1,000. In this particular case, it doesn't really matter what our constant is, right? Multiplying by 1,000 isn't going to make any difference. But if we were to combine this with a style, we might want to parameterize those. All right. And this is, if you remember when we did differentiation using PyTorch, we went ahead and did it backward. Okay? So what we're going to do is, each step, we're going to zero out the gradients. We're going to call the loss function, which we haven't looked at yet. No, sorry, which we have looked at yet. Yeah, it's that content loss there. We're going to then run backward propagation. We're going to just print out some stuff. And we're going to return the loss. Let me see, I'm trying to remember exactly. Yes, the optimizer takes care of then updating the variables we asked it to optimize. So it will go ahead, calling the loss function will cause us to do the forward pass, backward will do the backward pass, and then the optimizer itself will go ahead and update those values. And then we just go ahead and call step. Partial means a partial evaluation of the function. This just says apply the step function using the content loss we defined. And we go through and we get some iterations, and then we pull out of our variable the data. Right? In PyTorch 1, you don't have to do this, but in our version of PyTorch, data and tensors and variables are a wrapper around tensors. So .data pulls out the tensor. So pull it out, denormalize it, and then draw it. And what we get is a very sketchy house, but you can see that it's becoming a house. Monday, we will look at the notebook some more. And Monday, we're going to look at pulling out better layers and how to pull out all the layers from a model, because the way we worked isn't going to work for style, where we're going to get like multiple layers. We don't want to create multiple networks. We want one network that we can pull the layered information. I will be in my office until about 6 today, and I'll also be there Monday and Wednesday. If you're having any questions, I highly recommend you come to office hours. We can just spend time one-on-one. I don't have anything better to do.